So in this video, we're going to talk a little bit about the Nernst equation and also a little bit about the operation of batteries. So cell potential, or E0 cell, is also referred to as the electromotive force. The EMF can be thought of as being the force with which electrons are being pushed from the anode into the cathode. The cell potential is a measure of the spontaneity of the cell. The cell potential must be positive in order for a spontaneous redox reaction to occur. As cell potential is a measure of the spontaneity of a cell, it should be relatable to delta G and to Q and K. So for a spontaneous process, delta G naught must be less than 0, and the standard cell potential should be greater than 0. Previously, way back in Chemistry 162, we defined delta G naught as being the amount of energy that's available to do useful work. That is, this is the energy that we have left after we have paid the cost of increasing the entropy of the universe. When a voltaic cell moves electrons through an external circuit from the anode to the cathode, electrical work is done. We label this as work electrical. And so the delta G of a cell is just equal to the electrical work that it can do. And for a spontaneous process, this will be less than 0. That is, the cell will do work on the surroundings. The work done on the surroundings by a cell is equal to the negative of the charge that is transferred, which we give the symbol uppercase C, and the cell potential, or EMF, of the cell. So what is this charge business? Well, the charge transferred for an electrochemical cell is going to be directly related to the number of electrons that are transferred from the anode to the cathode. A single electron has a charge of 1.6 by 10 to the minus 19 coulombs. A mole of electrons has a charge of 9.65 by 10 to the 4 coulombs, or coulombs per mole. So this would be the charge that's transferred every time we move 1 mole of electrons. That number is kind of important, and we call it Faraday's number, and we give it the symbol uppercase F in honor of Professor Michael Faraday. So the total charge that's going to be transferred in a redox process will be the number of electrons that are moved multiplied by Faraday's constant. So the electrical work that is done by our cell is equal to the negative of the charge transferred multiplied by the cell potential. That should be an uppercase E there, but never mind, I'll fix that later. And we've just determined that the total charge that's transferred is equal to the number of moles transferred multiplied by Faraday's constant. So we can substitute that into our expression here. And so what we see is that the delta G of our cell is equal to the negative of the number of moles of electrons transferred multiplied by Faraday's constant multiplied by the cell potential. So when the cell potential is positive, delta G will be negative and the process will be spontaneous. So if we work through the dimensional analysis for this expression, delta G is a form of energy, so it should have units of joules, and then we can put in all of the units for the other components on the other side of the equal sign. So N has units of moles, Faraday's constant has units of coulombs per mole, and the cell potential has units of volts. So what we can see is when we cancel out moles, that a joule is exactly the same as a coulomb volt. So that's kind of something worth just sort of noting. When you do dimensional analysis here, if you end up with units of coulombs volts, you can substitute that for joules if you so desire. So a typical question might ask you to calculate delta G naught for a given cell. And what our strategy here is going to be is identify the number of electrons that are transferred and identify the cell potential of our cell. So this is asking for the standard Gibbs free energy exchange, so we can use standard reduction potentials to calculate the standard cell potential of our cell. So the zinc in this case is being oxidized, so it's the anode, and the copper in this case is being reduced from copper 2 plus to copper solid, so it's the cathode. So I go find values for the standard reduction potential of copper 2 plus, and then I find the value for the standard reduction potential of zinc 2 plus. And to calculate the cell potential, it's always cathode minus anode. So here I go, and just like we saw before, that the cell potential for this particular cell is 1.104 volts. Calculating delta G is an easy process now. I just have to think about how many electrons are being transferred. The copper 2 plus ion is being reduced by 2 electrons. The zinc metal here is being oxidized by 2 electrons. So 2 electrons are being transferred. So my N is 2. Faraday's constant, 9.65 by 10 to the 4. And then my cell potential, which I calculated previously, 1.104 volts. So I put all of that together and I get a negative number, negative 2.13 by 10 to the 5 joules. If I want, I can convert that to kilojoules. This is a pretty typical value for a chemical reaction. A few tens to a few hundreds of kilojoules is not to be unexpected. Here's another example. It says, what is the delta G naught for the cell based upon the following 2 electrodes? The reduction of mercury 2 by 2 electrons to give mercury liquid has a standard reduction potential of 0.851 volts. And then we've got here the standard reduction potential of zinc 2 plus ion by 2 electrons to give zinc, and that has a very negative standard reduction potential. So we know this guy is going to be reduced, it will be the cathode, and this guy here will go in the reverse direction, it's going to be the anode. So my cell potential is always cathode minus anode, and so in this case that works out to be 1.613 volts. How many electrons are being transferred? It's kind of easy to detect that. It's going to be 2 electrons. So my N is 2. Faraday's constant multiplied by my cell potential, and I get a bigger negative number in this case, minus 3.11 by 10 to the 5 coulomb volts or joules, and that's equivalent to minus 311 kilojoules. Sometimes it's not obvious the number of electrons that are being transferred, and how we can deduce that is by looking at how oxidation numbers are changing for given atoms. And effectively what we have to keep in mind is that the size of the change in oxidation number is equal to the number of electrons that are being transferred. So in this expression here, if I just look at the nickel, I begin with 2 nickel atoms that have oxidation number of 0, and I end up with 2 nickel atoms that have oxidation number of plus 2. So what has happened? One atom has gone from 0 to 2, a second atom has gone from 0 to 2, so that tells me that 4 electrons were transferred. As the nickel is being oxidized, this is a loss of 4 electrons. When I look at the oxygen, it's a little more complicated. On the reactant side, oxygen is in 2 different forms. There's elemental oxygen here with an oxidation number of 0, and then there's oxygen in the water with an oxidation number of minus 2. What happens is I end up with 4 oxygen atoms on the product side that all have an oxidation number of minus 2. So these oxygen atoms here, nothing happened to them. They just kind of, they just stayed in the same oxidation state. However, these 2 guys over here were reduced. Okay, so they went from 0 to minus 2. So one oxygen atom goes from 0 to minus 2, and then the second oxygen atom goes from 0 to minus 2. So that means that there was a change of 4. So there was a gain of 4 electrons in this case. The oxygen, its oxidation number reduced, so that indicates a gain of electrons. 2 oxygen atoms, each of them changed their oxidation number by 2. So what we determine, 4 electrons have been transferred. So if we hook up a copper zinc voltaic cell, we know what's going to happen. Electrons are going to flow from the zinc side into the copper side. So as this reaction progresses, the zinc electrode will get eaten away. It'll get converted into zinc 2+ ions, and the copper electrode will kind of grow as copper 2+ gets reduced to copper metal. So when will electrons cease to flow? Well, under one of two conditions. Either the zinc electrode gets eaten away to such an extent that it's no longer sitting in the electrolyte, then that will cause the reaction to cease. Or alternatively, if we have a big old piece of zinc here and that is not the limiting reactant, then if copper 2+ ions are the limiting reactants, once we've exhausted our copper 2+ ions, then electrons will cease to flow. So the answer to this question really is once the limiting reactant is completely consumed. So, and which in this case is when all of the zinc anode is consumed, or when all of the copper 2+ ions are consumed, the cell potential will drop to 0. So this man over here, Professor Nernst, he determined the relationship between the concentration of reactants and products and the cell potential. So in doing so, he formulated what is now known as the Nernst equation. And the Nernst equation is that delta G under non-standard conditions is equal to delta G naught, the delta G under standard conditions, plus RT log of the reaction quotient. So keeping in mind that the negative of the number of electrons transferred multiplied by Faraday's constant multiplied by the cell potential equals delta G, we can substitute for delta G with this term here. So when we do that, we end up with this expression here. And so now we have a formula that allows us to compute the cell potential under non-standard conditions, provided we know the standard cell potential, the number of electrons that are being transferred, the temperature of our system, and the value of the reaction quotient. So what does the Nernst equation predict will occur as reactants are consumed? Well, the standard cell potential doesn't change. That's a standard value. The number of electrons transferred doesn't change. That's determined by the chemistry of our system. The temperature of our system won't change normally, but Q will change. What will happen is reactants will be consumed and products will be created. So what's going to happen is reactants will decrease in concentration, products will increase in concentration. So as the cell reaction proceeds, Q will become bigger. So the term that we're subtracting away here is going to get bigger and bigger and bigger until this cell potential eventually drops to 0. So this is a good example of this effect. The standard cell potential of the voltaic cell based on the zinc-copper ion reaction is, and we probably should already know this, 1.104 volts. So this is when we have pure zinc, 1 mole per liter copper 2+, 1 mole per liter zinc 2+, and pure copper. But as soon as we hook this cell up, we're going to start consuming copper ions, and their concentration will drop to be lower than 1 mole per liter. And we'll start making zinc 2+ ions, and their concentration will grow to be bigger than 1 mole per liter. So the only time that we're going to have this exact cell potential is at the instant when we connect the cell. Any time after that, we will have a different value. And what will occur is that this cell potential will begin to drop. So this question asks, what is the value of the cell potential at 25 degrees Celsius once the copper 2+ ion concentration has dropped to 0.1 mole per liter, so 90% of the copper 2+ is being used up from the standard state, and the zinc 2+ concentration has increased to 1.9 mole per liter. So effectively what we're talking about here is 90% of the reactants have been consumed in this cell. So let's go ahead and calculate the cell potential. The cell potential is equal to the standard cell potential, 1.104 volts, minus RTNF. In this cell, 2 electrons are being transferred, so N is 2. Our temperature is given as being 25 degrees Celsius, but we need to express that in Kelvin. And the value of R that we use is the 8.314 value. So when we look at constructing the expression for Q, it's always going to be products over reactants, but we don't need to include the solids. So in this case, the expression for Q will be the concentration of zinc divided by the concentration of copper 2+. And that information is given to us. So plugging everything in, our standard cell potential, 1.104 volts, minus R times the temperature, 298.15 K, divided by NF, multiplied by log of the zinc ion concentration divided by the copper ion concentration. And sure enough, the cell potential has gone down by a little bit. Now, it's interesting to note, this is sort of the value that we get when everything is 1 mole per liter. And then after we've consumed 90% of our copper ions, 90% of one of our reactants, the cell potential has barely moved. It's only moved by 0.04 volts. It's effectively, it's almost the same value to, or it is the same value to 2 significant figures. And that's because there's a logarithmic dependence on Q. So what we tend to see with cell potentials is that they tend to maintain pretty much like the same value all the way across, and then very quickly they plummet to 0. And so you've probably noticed this with your cell phone, that everything seems to be good for a while and then boom, it just drops off to nothing. Or if you've had the unfortunate scenario of having a car that's kind of hard to start, it seems like the car is turning over just fine, that the battery is doing a great job, the starter is sort of working, and then all of a sudden, boom, you have no car battery and you're in trouble and begging for someone to jump start your car. So on that note, we're going to have a look at what is referred to as the lead acid battery, which is exactly the type of battery that you have in your car. In the lead acid battery, you have 2 solid materials. You have solid lead, which is in the form of lead plates, and then you have lead 4 oxide solid, which is normally a coating on these lead plates. The whole thing is immersed in sulfuric acid, and that gives it its name as being the lead acid battery. The products of this reaction are lead 2 sulfate and water, and it has a cell potential of a little over 2 volts. So in your car you have a 12-volt battery, and that's because they've got 6 of these cells connected to one another, 6 times 2, giving you approximately, or giving you 12 volts. Something to keep in mind is that when the cell reaction reaches chemical equilibrium, delta G will equal 0, which means that the cell potential itself also equals 0 and Q equals K. So we can actually use that to create an expression relating the cell potential to K. So at equilibrium, the cell potential is equal to 0 and Q is equal to K. So 0 is equal to the standard cell potential minus RT on NF log K. So just bringing the RT NF log K, isolating that by itself, what I get, the cell potential is equal to RT NF log K. So if I can measure the cell potential for a reaction, I just put it into this expression and I very quickly get K. So here's an example calculation using the Nernst equation. It says nitric oxide may be produced from the following reaction. Some of you guys were doing this in the lab. We take 3 moles of copper solid, react it with 8 moles of acid, in the presence of 2 moles of nitrate anion, and what happens is we end up forming 2 moles of nitrogen monoxide gas, which is a nice brown color, and the copper solid is oxidized to copper 2+, which dissolves into aqueous solution, giving it a nice blue color. And it's kind of a fun reaction to do. It takes a little while to kick off, but it's kind of, you get nice bright changes in color and all of this sort of brown gas being formed. This question is asking us to determine E0 for this reaction. We're going to use standard reduction potentials to do this. Then we're going to calculate the cell potential when the hydrogen ion concentration has dropped down to 0.1 mole per liter and the nitrate ion concentration is 0.025 moles per liter. The copper ion concentration is 0.0375 moles per liter, and the partial pressure of NO, because it's a gas, is 0.0015 atm. And you can see we've got some pretty sort of awkward coefficients in here. And so that's going to lead to a fairly, sort of like awkward expression for Q. Okay, so what's being oxidized, what's being reduced? So the copper is being oxidized from copper 0 to copper 2+. So that's our anode reaction there, and the standard reduction potential for the reduction of copper 2+ ions is 0.342 volts. Okay, what is being reduced now? What is our cathode reaction? So nitrogen in nitrate has an oxidation number of +5. Nitrogen in NO has an oxidation number of +2. So nitrogen is being reduced by 3 electrons. And here, this is the reduction reaction that's written here. It's the cathode reaction. So nitrate plus 4 moles of acid plus 3 electrons reduces to nitrogen monoxide and water, and the standard reduction potential for this one, 0.96 volts. So as we know, the cell potential is just the cathode reduction potential minus the anode reduction potential, which in this case works out to be 0.6181 volts. So we've got E0, and now we're going to calculate Ecell when there's been significant, or when the concentrations and partial pressures are very, very different from the standard states. So the non-standard state cell potential is equal to the standard state cell potential minus RT on NF log Q. So how many electrons were being transferred? 3 moles of copper being oxidized by 2 electrons. So that tells me that my N, 3 times 2, is 6. I have my cell potential from my previous calculation. We're going to, it says here that the temperature is 298, so there we are, and our R value is 8.314. So now we've got to multiply this by log Q, so it is products over reactants. We can ignore pure liquids and solids, so we just have to deal with the NO and the copper 2+ as our products, and then we've got the hydrogen ions and the nitrate anion as our reactant. So here we are. So this is it. So it's going to end up being the pressure of NO, and that needs to be squared, multiplied by the concentration of our copper ions, and that needs to be cubed, divided by the concentration of NO3-, and that needs to be squared, multiplied by the concentration of H+, and that needs to be raised to the power of 8. This doesn't have the square here for some reason. So when I put all that math in, what do I get for my answer? 0.580, which is a tiny little bit less than what we had for our standard cell potential of 0.628 or 0.62 volts. Okay, so summarizing, the charge transferred in a redox process is given by the number of electrons transferred multiplied by Faraday's constant. A delta G0 for an electrochemical process is just equal to the negative of the number of electrons transferred multiplied by Faraday's constant multiplied by the standard cell potential. As our cell runs, the concentration of reactants will decrease and the concentration of products will increase. How this affects the overall cell potential is described by the Nernst equation. Once we come to equilibrium, the cell potential will drop to 0 and Q will become equal to K, and using that relationship we can derive this expression relating the standard cell potential to K. Okay, so that concludes this video. Sorry about the little mistake with my login for iTunes or something or other popping up in the middle there, but I can't be bothered editing it out. It's almost 11 o'clock at night and I need to go to bed. Okay, I'll see you all on Monday.